This lesson is intended to reach a pre-calculus student just starting out. Usually we talk about a bit of algebra at the beginning of pre-calculus, so this is the algebra unit lesson 1, simplifying algebraic expressions. So where I teach, we have these outcomes called student learning outcomes, or SLO, and this is something that is given to us to make sure that the students know before they move on to the next course, which generally is calculus. So the SLO that relates with this lesson is demonstrate understanding and knowledge of properties of functions. And more specifically, underneath this SLO, we have this learning objective, which the professors are asked to come up with. And so the learning objective here is that the students will simplify various algebraic expressions using factoring, finding an LCD, as well as other techniques. So let's go ahead and jump right in. First things first, it might be helpful to know what an algebraic expression is. So here we have a definition, algebraic expression, a mathematical phrase that can contain numbers, variables, and operators. Operators just meaning like addition, subtraction, multiplication, division, parentheses, exponents. It pretty much sounds like your order of operations. So you can see now that below there are some examples of algebraic expressions. So here we have 3a squared x minus 14. So you can see a couple numbers like 3, and this is what we would call a coefficient because it's being multiplied to some variables, whereas 14 would be a constant because there are no variables being multiplied to that number. So an exponent, the squared, is an operation. Hiding in here between the 3 and the a is a multiplication, so that's an operation. There's another multiplication here between a squared and x, that's an operation, subtraction operation. And you can take a look at these other two. I just want to point out that this set of parentheses means that there's some sort of operation happening between this negative 13 or this minus 13 and this set of parentheses, and that is multiplication. So normally known as distribution, you would just distribute this negative 13 to each term on the inside. And finally down here, we have some division happening. So there are little fractions on the top and the bottom of a larger fraction. So these are what algebraic expressions can look like. As mentioned on the first slide, you will need to know how to factor. And as far as I can remember, there are 5 different types of factoring that are needed to pretty much get through the entirety of pre-calculus. The first of which being a GCF, or a greatest common factor. And this is when you divide each term by the largest number possible, or divide each term by the smallest exponent of variable that you may have. If you don't understand what this means, you will see some examples in the coming slides. So that's the first one, greatest common factor. You should always check for this first. Check for GCF first. The second type of factoring, I'm just going to list as factoring. It goes by 100 different names. There's the AC method, there's the split B method, there's the ladder method, there's a 2x2 box method. There is slide and divide, or divide and slide, or however it goes. And whichever one works for you, works for you. I will use the split B method, but I am open to all of them. The third type of factoring is factoring by grouping. And you'll see this on the next slide, so I'm not going to go too far into it. The next one is the difference of squares. And that looks like this, where you can have something squared minus something else squared. And this subtraction is super important. It's part of the name, difference of squares. So something squared minus something else squared. And it turns out that factoring is relatively easy comparatively to some of these others. And the last one would be either the sum or the difference of cubes. And that would look like something cubed, either addition or added to or subtracted from another thing cubed. So in addition to these, you will need some working knowledge on how to find an LCD and how to multiply polynomials, as well as some various other tools used in algebra. I'd say it's time to look at some examples of what it means to simplify an expression. Simplify the following algebraic expression. On this slide, we have two algebraic expressions, and part of simplifying things means factoring, so that's a big one. So this, we will need to factor this to simplify, we will need to factor this to simplify. In order to simplify or factor this left expression, first of all, again, you can see there are numbers, there are operators, being multiplication here, subtraction, multiplication, another subtraction. A square is an operator. And then we also have variables being x. And something similar is happening over here. Here we actually have an addition. So these are both algebraic expressions. And in order to factor, there's a very sure way to do this. And that is to remember that you start out with ax squared plus bx plus c, and you find a, b, and c, all with the sign that is included with the number. So in this case, b is negative 17, and c is negative 21, and a is a positive 8. So I can do this little AC, this little t-chart here, B. And what I want to do is multiply A times C. And that's 8 times negative 21 is negative 168. And B is negative 17. So the goal here is to find two numbers that multiply to give you negative 168, and those same two numbers that when you add them together, you get negative 17. And you can think about it and find a bunch of different factor pairs, but eventually you're going to come to negative 24 and 7. When you multiply negative 24 times 7, you do in fact get a negative 168. And when you add 7 and a negative 24, you will get a negative 17. This is where most of the work comes from factoring a trinomial. All right, so what do you do with this? You will take the middle term, negative 17x, and you will split it apart into two different terms, being negative 24x plus 7x. The first and last term come down for the right. So 8x squared here, minus 21 here. And we split these apart very specifically. So now what we will do is we will group the first two terms together and find a common factor. And we will group the last two terms together and find a common factor over here. Usually it's easier to find the common factor of the last two terms, so I'm just going to do that this time, first time. And I want to say the common factor here between these last two terms is 7. And in fact, it's going to be a positive 7. The sign of the first term where you are common factoring will be the sign of the common factor. So positive 7. And since we're factoring, we have to figure out what will go left in this set of parentheses. One thing to keep in mind is that since this group has 2 terms, after we common factor, what's left over inside this set of parentheses will still have 2 terms. The number of terms will match. So if you come up here and divide both of these by the common factor, you end up with x minus 3. And you can check. It takes just a few seconds to check. 7 times x is 7x. 7 times negative 3 is negative 21. That common factor works out really nicely. All right, let's take a look at these first 2 terms here. Here we have 8x squared minus 24x. With this one, the numbers, we can divide both of these numbers evenly by 8, and that's the largest number. So we are looking for that number, so 8. And both of these terms have an x, so we can also common factor an x. So again, since the first term here is positive, our common factor is positive, and then we just come up here and divide by 8x. And then we can find out what goes in this set of parentheses will end up being x minus 3. Well, at this point, we have 2 terms. We have this one term in blue and this other term in purple. And they both share something in common, being the x minus 3. So we can just do this again. What do they have in common? That x minus 3? If we divide by x minus 3, the entire x minus 3's will cancel, leaving us with 8x plus 7. And that's what goes in the other set of parentheses. And we are done factoring. So if you simplify this, you will end up with x minus 3 times 8x plus 7. Now in this other example here, you can see that this one's a little bit different because here we started with 3 terms and we use this version of factoring here. But this version of factoring, you have already seen. Anytime you see 1, 2, 3, 4 terms and you're asked to simplify, that generally means factor. But we are going to do something here very similar to what we were doing here. Here we had 1, 2, 3, 4 terms. But even before we get into factoring this, like we did this, grouping the first 2 and grouping the last 2 terms, it is always important to check for a common factor first, a greatest common factor first. So in this case, if you look at all 4 terms, can all of these terms be divided by some number or variable other than 1? And in this case, every term can be divided evenly by 5, and that is the largest common factor, so we call it the greatest common factor. So what we can do is we can come up here and divide all of these by 5. And what that'll do is the GCF will come out to the front, greatest common factor, GCF, will come out to the front, and we'll just divide all of those terms. So x cubed plus 2x squared minus 4x minus 8. And what this does is it takes care of some factoring that we would have to do later. It's, in my opinion, always better to check for a greatest common factor to begin with than trying to find it later. So from here, the greatest common factor will always be a part of our answer. So I know way down here, when I'm done factoring, I'm going to have 5 in my answer. So from here, we are going to group the first two and the last two, just like we did over here. And we will find some more common factors. So here, x cubed and 2x squared, these both have an x squared that we can common factor out. So I'm not going to worry about this 5 until the very end. I'm just going to work inside the set of parentheses at the moment. So that means x squared. That means there will be something here. So if I come up and divide this by x squared and divide this by x squared, that means I'm left with x plus 2. And the first term here in this group of 2, this x cubed plus 2x squared, is positive. So my greatest common factor is positive. Now when we look at these last two, really quickly, my first term is negative. That's a negative 4x minus 8. So when I find a greatest common factor here in these second two, it's going to be a negative value. So you can see there's a negative 4x minus 8. You can divide both of those numbers by 4. But in fact, we're going to be doing it by a negative 4. And when you do that, you're left with x plus 2 inside the parentheses. And again, you can see that there are only two terms here. There's this one, and there's this one. So what we have here is they both have an x plus 2 in common and x plus 2 in common. So we can kick that x plus 2 out to the front. So x plus 2. And we're left with an x squared minus 4. And it looks like we're done factoring, except this can be factored again by the difference of squares. And what that means is I can create equal groups. So if two equal groups. So with this first term, x squared is x times x. Well, those two groups are equal. And 4, I can break down into 2 times 2. So remind you, this is all multiplication happening down here. So x times x is x squared, 2 times 2 is 4. They're separated by a minus sign, and that's very important. Difference of squares, difference meaning subtraction, and squares meaning you can break these apart into equal groups that are multiplied. So x and 2. So for this part of factoring, it can break down into 2 more sets of parentheses. And you'll notice that since the first term here can be broken down to x times x, the x's come first. And since the second term, the 4, can be broken down in 2 times 2, the 2's come second in each set. One gets plus, one gets minus. But this x plus 2 is still here. Finally, we're done, right? Well, it's close. Anytime you have two or more of the same factors, you can always simplify these into one factor raised to a power. So here's the example. We have x plus 2 and x plus 2. We don't really need to write it twice, just write it once. X plus 2. How many times, or how many x plus 2's are being multiplied? 1, 2. So this gets an exponent 2. And then finally we have that x minus 2 coming along for the ride, and this down here is your final answer for factoring or simplifying this algebraic expression. Simplify the following algebraic expression. On this slide, there's just one example. You can see it's x to the 8th power minus 16. And this expression only has 2 terms. And so this is what leads me to believe with seeing the subtraction sign as well, that this will use the difference of squares factoring. Now, on the last slide, you saw something, I think it was x squared minus 4. And you look at that and you see x squared, and you can take the square root of 4 pretty easily. So we can easily break these down into two equal groups that are being multiplied together. So the difference of squares, even though squares in the title, does not only mean that you can do it if you have something squared. It turns out that I can break this 8x to the 8th power into two equal groups of x to the 4th times x to the 4th. And this 16, I can break that down into two equal groups that are being multiplied into 4 times 4. So now I'm going to set up these sets of parentheses the same way I did. The x squareds come first, or x to the 4th come first, so they will be first here and here. And the 4s come second, so I'll put one there and there. One gets plus, one gets minus. And you already saw something like this in the last example where, okay, I've done a difference of squares factoring. That's it, I don't want to do any more, but you have to check that whatever it is that you factored can't be factored again. So if you look at this first polynomial, x to the 4th can be broken down into x squared, and 4 can be broken down into 2 and 2, but this is not a difference of squares. This is a sum of squares. So there is no nice way to factor this. However, in this polynomial, we do have a difference of squares. So we can break this x to the 4th down into x squared, and we can break this 4 down into 2 times 2. So now I will have two new sets of parentheses, each starting with an x squared, and each ending with a 2. One gets a plus, one gets a minus. And this x to the 4th plus 4 just comes along for the ride. This is our final answer. So you might think, well, hey, this I can break down into x and x, but how can you nicely break down 2 into two numbers that get multiplied together that are the same thing? Right? 2 is 2 times 1. Those are not the same thing. 1 times 2, those are not the same numbers, right? It doesn't matter what order you do it in. Those are not the same numbers. So how would you break that down? Well, it's not as easy as 16 becoming 4 times 4 or 4 becoming 2 times 2. So because of that, we stop. And this is the simplification of this starting algebraic expression. Simplify the following algebraic expression. In this example, and yes, this is one example, we get our first taste in this video with LCDs. So you can see that there are some denominators like y squared, y squared, and x squared. And it would be really awesome if we could just go ahead and get rid of all of those tiny little denominators that are within the fraction. We might be able to, at the very end, get rid of this entire denominator and just end up with an expression, but that remains to be seen. So let's find the LCD of all of those little fractions, and it ends up being x squared, y squared. Once you have this LCD, what you will do is multiply the top and bottom of the big fraction by x squared, y squared. Now from here, what will help you a lot and what will get rid of these fractions is distributing this x squared, y squared to each term in the numerator and to each term in the denominator. And the whole point of multiplying the top and bottom by this LCD is to get rid of these tiny little denominators. So when you multiply this times this fraction, the y squareds will cancel, leaving you with an x times an x squared, which if you multiply x times x squared leaves you with an x cubed. When you multiply this to the second fraction up here, the x squareds will cancel, leaving you with a y times a y squared, which is a y cubed. And there is a subtraction in between them. There it is right there. That's the same subtraction. Now in the denominator of the big fraction, when you multiply this times this fraction, the y squareds will cancel, leaving you with an x squared times 1, which is just x squared. And when you multiply this to this fraction here, the x squareds will cancel, leaving you with 1 times y squared, which is just y squared, and it's still separated by a subtraction. So finding an LCD and multiplying by it got rid of all these tiny little fractions, but you can see we still have one fraction to work with. And again, whether or not this fraction ends up disappearing is unknown. So we can just go through, and if we still have a fraction at the end, we still have a fraction at the end. So now, in order to simplify, this now means factoring. So the factoring of the denominator using difference of squares, and in this video I think you've seen enough examples of that, will turn into x plus y times x minus y. And if you need an explanation, you can go back to one of the previous examples with difference of squares to see how that's done. In this top portion of factoring, this is what was going to use the difference, and that's because of the subtraction sign here, the difference of cubes. And so the difference of cubes will look something like this. If you have something cubed minus something else cubed, that will be the first minus the second in the first set of parentheses. So it's almost like you get the first set of parentheses for free. You just write down what you see without the exponents. And in the second set of parentheses, you get a squared plus ab minus, plus b squared. So substituting the x's and y's in for the a's and b's, you end up with x minus y times x squared plus xy plus y squared. All right, so there, the top has been factored, the bottom has been factored, and generally when you're doing difference of cubes or sum of cubes factoring, this second polynomial with the variables squared or the higher exponents will not factor again. So now we have something that is identical in the top and the bottom, and that is x minus y. So we can reduce that entire factor away and be left with our final answer, x squared plus xy plus y squared, all over x plus y. Simplify the following algebraic expression. And with this algebraic expression, you can see that we have x squared minus 4y squared minus 6x plus 9 all over this rational expression in the denominator, 1 over 2y minus 1 over x minus 3. Where to begin? Well, it looks like we have some fractions in the bottom, and so I would really like to get rid of those, so I'm going to multiply those by an LCD. And the LCD here is going to be 2y times x minus 3. So what I'm going to do with this is I'm going to multiply the top and bottom of this fraction by 2y times x minus 3. And in the numerator, I'm not going to distribute out the 2y times x minus 3. Part of simplifying that we'll do in a second is making sure that you have things in factored form. And so this is already factored out of this expression, so I don't want to distribute it back in there to try to factor it out again later. So the new numerator here is x squared minus 4y squared minus 6x plus 9. And that's what you see here, but I want to rearrange everything so that the x's are first and the y's come second. So here we go with the x squared minus 6x plus 9 minus 4y squared. And I'm going to put these parentheses here, and I'll explain why I'm doing that in a moment. But then this is all being multiplied by 2y times x minus 3. In the denominator now, there is, let's see, it'll be x minus 3. And that's because when you distribute this least common denominator to this fraction, the 2y reduces away, leaving you with just an x minus 3 times 1. And when you distribute this same LCD to this fraction, the x minus 3 reduces away, leaving you with a minus 2y. Alright, so this is the fraction as it stands right now. And I mentioned that I was going to explain why I put these parentheses around the x squared minus 6x plus 9. I do that because I realize that the x squared minus 6x plus 9 can be factored. So I'm going to do that off to the side here really quick. That x squared minus 6x plus 9 can be factored into x minus 3 times x minus 3, which can be rewritten as x minus 3 squared. So I'm going to write this fraction again with this substituted in for this. So this fraction becomes x minus 3 squared minus 4y squared times 2y x minus 3 all over x minus 3 minus 2y. So again, right now I'm just simplifying what's in the numerator, and I don't need to simplify anything here because this is all already factored, and I don't want to distribute because that's the opposite of factoring, so I'm factoring what I can in this set of parentheses. Now, upon factoring this and substituting it in, you can see that now there is a difference of squares. It's this thing squared minus this thing squared. Cool. Let's factor that off to the side. So when you see x minus 3 squared minus 4y squared, I know that each factor will get an x minus 3, and each factor will get a 2y. So I know now that this set of parentheses here will factor into x minus 3 plus 2y and x minus 3 minus 2y. So I'm going to rewrite this fraction again. So here is the new fraction way down here. And upon factoring this into a difference of squares, you can see now that we have a factor that matches in the numerator and the denominator, and those can be reduced away, leaving you with your final answer of x minus 3 plus 2y times 2y times x minus 3.